Number theory is the study of integers and their properties, relationships, and patterns. It explores fundamental questions about divisibility, prime numbers, congruences, and Diophantine equations. Often called the queen of mathematics, it forms the purest branch of mathematical inquiry. Its foundations include divisibility and the Euclidean algorithm, prime numbers, and the fundamental theorem of arithmetic, which states that every integer greater than 1 can be uniquely expressed as a product of primes, modular arithmetic and congruences, Diophantine equations such as Fermat's last theorem, and the distribution of primes studied through the prime number theorem. For example, Fermat's little theorem states that if p is prime and a is not divisible by p, then a raised to p minus 1 is congruent to 1 modulo p. Advanced topics include analytic number theory, which uses complex analysis to study prime distribution, algebraic number theory, which generalizes integers to algebraic number fields, and computational number theory, essential in modern cryptography. The Riemann hypothesis, one of mathematics' deepest unsolved problems, concerns the distribution of prime numbers and remains a central question in the field. Abstract algebra studies algebraic structures and their properties through axioms and formal operations, generalizing arithmetic to abstract systems. Unlike elementary algebra, it focuses on the structure itself, rather than solving equations. Its fundamental objects include groups which capture symmetry through a set with an associative operation, an identity element, and inverses, rings, which combine two operations satisfying distributive properties, fields, which are rings where every non-zero element has a multiplicative inverse, and modules and vector spaces, which extend these concepts. Key results include Lagrange's theorem on subgroup orders, the fundamental theorem of finite abelian groups, Silo theorems for analyzing group structure, and Galois theory, which connects field extensions to group theory and resolves classical problems about polynomial solvability. Abstract algebra provides the language for modern mathematics, appearing in algebraic geometry, number theory, topology, and theoretical physics. Linear algebra studies vector spaces, linear transformations, and their representations through matrices. It provides the framework for understanding multidimensional spaces and linear relationships between them. At its foundation lie vector spaces over fields, satisfying axioms of closure, associativity, and distributivity, linear transformations and their matrix representations, bases and dimension which formalize coordinate systems, and eigenvalues and eigenvectors. Solutions to the equation AV equals lambda v. Core concepts include determinants, which measure scaling factors and determine invertibility, inner product spaces and orthogonality, which extend Euclidean geometry to abstract spaces, the spectral theorem for symmetric and normal matrices, singular value decomposition, and Jordan canonical form. It extends to infinite dimensional spaces in functional analysis and underpins quantum mechanics where states are vectors in Hilbert spaces. Real analysis provides the rigorous foundations for calculus, formalizing notions of limits, continuity, and convergence through epsilon-delta definitions. Unlike calculus, it emphasizes proofs and the logical structure underlying differentiation and integration. Its foundations rest on the completeness of the real numbers, captured by the least upper bound property, sequences and their convergence, including Cauchy sequences and the Bolzano-Weierstrass theorem, continuity defined through limits ensuring that small changes in input produce small changes in output, differentiation and the mean value theorem, and Riemann integration. Advanced topics include uniform continuity and uniform convergence, the Lebesgue integral, which generalizes Riemann integration, metric spaces, providing abstract settings for analysis, and measure theory, which formalizes the notion of size. Real analysis forms the theoretical backbone of modern mathematics, ensuring that intuitive concepts rest on logically sound foundations. Complex analysis studies functions of complex variables, revealing deep connections between analysis, geometry, and number theory. Unlike real analysis, differentiability in the complex plane is remarkably restrictive, leading to powerful theorems. Its core concepts include analytic functions, which are complex, differentiable, and satisfy the Cauchy-Riemann equations, contour integration, and Cauchy's integral theorem, which states that the integral of an analytic function over a closed curve is 0. Residue theory for evaluating integrals through singularities, conformal mappings, which preserve angles and provide geometric insights, and Laurent series expansions around singular points. For example, the Cauchy integral formula states that f of z equals 1 over 2p I times the integral over gamma of f of zeta over zeta minus z d zeta, expressing function values through boundary integrals. Key results include Liouville's theorem stating that bounded entire functions are constant, the fundamental theorem of algebra proven through complex analysis, the maximum modulus principle, and the Riemann mapping theorem. Complex analysis applies to number theory through the Riemann zeta function, providing elegant solutions to problems intractable in real analysis. Topology studies properties of spaces preserved under continuous deformations, such as stretching, bending, and twisting, without tearing or gluing. It abstracts the notion of closeness without requiring distances, focusing on qualitative rather than quantitative structure. At its foundation lies the topological space, defined by a set X and a collection of open sets satisfying axioms of closure under unions and finite intersections, from which arise concepts such as compactness, generalizing closed and bounded sets, connectedness, determining whether spaces can be separated, completeness in metric spaces, bases and subbases for generating topologies, and separation axioms such as Hausdorff and normality. For example, the real line with the standard topology has open sets consisting of arbitrary unions of open intervals. Advanced topics include quotient spaces and identification topology, product spaces and Tikhonov's theorem, metrization theorems determining when topologies arise from metrics, and properties of function spaces. General topology provides the foundation for differential geometry, algebraic topology, and functional analysis, formalizing continuity in abstract settings. Differential geometry studies smooth manifolds and geometric properties using calculus and linear algebra. It extends classical geometry to curved spaces, providing the mathematical framework for Einstein's general relativity. Its foundations include smooth manifolds, which locally resemble Euclidean space, but have global structure, tangent spaces, and tangent bundles, formalizing velocities and directions, differential forms and exterior calculus, generalizing integration to manifolds, and Riemannian metrics, which define distances, angles, and curvature. Central concepts include geodesics, the shortest paths between points, generalizing straight lines, the Riemann curvature tensor, which measures how manifolds deviate from flatness, Gaussian curvature for surfaces, connections and covariant derivatives, and Lie groups, which combine group structure with smooth manifold structure. Deep results include the Gauss-Bonnet theorem relating curvature to topology, the classification of surfaces by genus, and the Hodge decomposition. Differential geometry connects pure mathematics to theoretical physics, particularly in gauge theory and string theory. Algebraic topology uses algebraic structures to study topological spaces, assigning groups, rings, or modules to spaces in ways that preserve topological equivalence. Among its central constructions are homotopy groups, particularly the fundamental group pi sub 1, which captures loops in a space, homology groups, which measure n-dimensional holes and are computed through chain complexes, cohomology groups, dual to homology, and forming ring structures, and the exact sequence, a powerful tool for computing invariance. Key theorems include the Brouwer fixed-point theorem, the fundamental theorem of algebra proven topologically, the classification of surfaces through Euler characteristic, excision, and Mayer-Vietoris sequences, and Poincaré duality for manifolds. Advanced topics include spectral sequences, K-theory, and homotopy theory. Algebraic geometry studies solutions to systems of polynomial equations, called varieties, using tools from commutative algebra and category theory. It unifies algebra and geometry, allowing geometric intuition to solve algebraic problems and vice versa. Its foundations rest on affine varieties, defined as zero sets of polynomial ideals, projective varieties, which compactify affine varieties by adding points at infinity, morphisms between varieties, structure sheaves providing local algebraic data, and schemes, which generalize varieties and allow nilpotent elements. For example, the affine variety V of I in affine n-space over K consists of all points where polynomials in ideal I vanish simultaneously. Central concepts include dimension theory, Hilbert's Nullstellensatz connecting ideals and varieties, coherent sheaves and their cohomology, divisors and line bundles, and intersection theory. Deep results include Bézout's theorem on intersection multiplicities, resolution of singularities, Riemann-Roch theorems, and Grothendieck's schemes revolutionizing the field. Functional analysis studies infinite-dimensional vector spaces, particularly spaces of functions, and linear operators between them. It generalizes linear algebra and provides rigorous foundations for quantum mechanics and differential equations. Its core objects include Banach spaces, complete normed vector spaces such as L raised to P spaces, Hilbert spaces, complete inner product spaces generalizing Euclidean space, bounded linear operators and their spectra, weak and strong topologies, and dual spaces consisting of continuous linear functionals. For example, the space L, raised to 2 of square integrable functions with inner product defined by integration, forms a Hilbert space fundamental in quantum mechanics. Key theorems include the Hahn-Banach theorem on extending linear functionals, the open mapping theorem and closed graph theorem, the uniform boundedness principle, the spectral theorem for self-adjoint operators, and the Riesz representation theorem. Advanced topics include operator algebras, C-star algebras, distribution theory generalizing functions, and Sobolev spaces. Functional analysis bridges pure mathematics and mathematical physics, providing the language for quantum field theory and partial differential equations. Category theory provides an abstract framework for mathematics, studying mathematical structures through their relationships rather than internal properties. It unifies diverse mathematical fields by identifying common patterns and universal constructions. At its foundation lies the category, consisting of objects and morphisms, between them satisfying associativity and identity axioms, functors, which map between categories preserving structure, natural transformations, which relate functors while respecting their structure, and universal properties, characterizing objects by their relationships. Central concepts include limits and colimits, generalizing products and coproducts, adjoint functors, pairs of functors related through natural bijections, monads, encoding algebraic structures abstractly, unit lemma, showing objects are determined by morphisms into them, and equivalence of categories. Mathematical logic and set theory provide the formal foundations for all of mathematics, establishing axioms, proof systems, and the notion of mathematical truth. Set theory describes how mathematical objects are constructed, while logic formalizes valid reasoning. Its pillars include axiomatic set theory, particularly Zermelo-Fraenkel with the axiom of choice ZFC, ordinal and cardinal numbers, measuring sizes of infinite sets, the continuum hypothesis concerning the cardinality of the reals, first-order logic with quantifiers and predicate symbols, model theory studying relationships between formal languages and their interpretations, and proof theory analyzing formal derivations. Key results include Gödel's incompleteness theorems, showing limitations of formal systems, the independence of the continuum hypothesis and axiom of choice from ZFC, forcing and large cardinal axioms extending set theory, and computability theory, defining algorithmic solvability through Turing machines.